Yeah. Okay, welcome on Zoom, welcome in the room. We have Maria Pacheco here. Let me try the introduction without reading it. So correct me if I'm wrong, but she's a PhD candidate in the computer science department at Purdue University. And she's working on neural symbolic methods for natural language processing and discourse. And before that, so she's from Caracas, Venezuela, and she worked there for a couple of years in startups as a data scientist and software engineer. And she also received the Microsoft 2021 research dissertation grant. Yeah, so yeah, we're very happy to have you here. Welcome, and yeah, please.
Thank you so much. So hi everyone, I'm really happy to be here. So I'm going to talk today about neural symbolic modeling for this course. But before I sort of jump into it, I want this to work. So before I jump into it, I want to talk about sort of the current trend in NLP. So with the adoption of deep learning, we've sort of had led to impressive advancements. And I have just here sort of example that we, some of us are familiar with and we've seen around, which is some sort of a person interacting with a large-scale language model like GPT-3, and they're trying to have some sort of interaction. And it's pretty impressive, when we play around with these methods, what they can do without explicit training. After having been trained on sort of large amounts of training data, they can really elicit really sort of natural sounding language that, it's pretty impressive. And the way most of these methods work is that they map the raw inputs, in this case, tons of language, to outputs by encoding the language structure in sort of a hidden high dimensional space that we don't make explicit, but just sort of, learn through data. And however, these models are really hard to train. So if we look at sort of the trend that we, since 2018, since BERT was introduced to right now, and I guess we've already expanded this already. In 2018, we were looking at a handful of billions of parameters, and it just, 2 years, GPT-3 was already in the scale of hundreds of billions of parameters. So this has two main consequences. The first one is that they really need tons of data to be able to be learned. And we're talking about sort of internet scale amounts of data. So every sort of textual resource that you can find has been fed into these models to be trained. And therefore, they're really computationally expensive. So not a lot of institutions can reproduce training these models from scratch. And the way we've gone around this is that the fact that they can be pre-trained and then sort of store some of this data allows people to download the pre-trained weights and then fine-tune them on, smaller amounts of data. And this is what a lot of the current NLP research does, so sort of leverages on these models. But, beyond sort of the computational consequences and the fact that they work really well, there are other downsides that come with the adoption of end-to-end deep learning methods. And the first one that, we've heard a lot about is that there's essentially unexplainable black boxes. So, they have tons of attention heads with tons of parameters. So really understanding what they're capturing and what they're learning, it's really hard for us to do. And this has other consequences, beyond sort of being able to understand. Sometimes when people design benchmarks to test these models, it's really hard to appreciate what they're learning. We can be misled by thinking they're capturing what we want them to capture, or learning what we want them to learn, if we're not careful about the way we design sort of the benchmark data set. And a motivated example here is this work that my and collaborators call Right for the Wrong Reasons, in which they tested sort of BERT-like models on the entailment task. The entailment task, essentially, you have two pieces of two sentences in natural language, and you want to identify whether one entails the other one. And what they found is that the benchmarks that were designed for this task, it had all of these heuristics like overly represented on the positive classes. So things like high lexical overlap between sentences, or the fact that a subsequence would be embedded, in the other text, or really overlap between each other's constituent parse trees. And they created this sort of adversarial model in which they try to reproduce negative examples that reuse these heuristics. And it really broke a lot of the methods that previously were reported to be very good. This doesn't mean that we can't find ways to get around it by design, better data sets, or, some people argue, but the fact that they're so unexplainable, makes us a lot of times be captive of these situations if we're not careful, because we design a test set, a training set, we feed them to these models, we don't really understand what they're capturing, they seem to be performing well, but it's really hard to sort of capture exactly what's going on. If we take a step back and think about sort of AI, prior to the deep learning boom, symbolic inferences was a more natural way to express and reason over problems. And the go-to example is like, if I have a data set of facts and I know things, for example, that people are mortal, and I also know that Socrates is a person, then I can infer new facts such as Socrates is also mortal. And there was a lot of work done in this space on how to learn these things from data, or how to capture the uncertainty in this databases and symbolic inferences. And I guess the drawback that the symbolic methods had, and that deep learning sort of came to take cover, is it's really hard to account for the noisy high dimensional space of language. So if we were to encode every word form in a symbolic structure, or try to capture context by just using symbolic structures, then it's really hard to generalize to language. But what I want to motivate in this talk is, why not combine the best of both worlds? So can we find a way in which you can use neural methods for what they're good at, by training them on expressive models on large amounts of data that capture sort of these patterns in raw data, but at the same time map these neural representations to symbols and then explicitly reason over higher level patterns. And I wanted to talk a bit about what does this mean then in the context of discourse. So when we think about discourse, we usually think about three components. The first one is just the language itself. So it's essentially all the written and oral material that you have for the language. Then there's sort of the practice of the language. So anything that takes place between participants during an interaction, for example, the turn taken during a conversation. And then there's the broader context, which is essentially everything that is available to the participants that contextualizes the language, but that might not be explicit in the language itself. So if I were thinking about sort of what this would look like, in a neural symbolic method, I want to start with a simple example from sort of the grounding task, in which we have an utterance without any textual context, something just like close it. And then we have some real world context that sort of contextualizes this. So let's say in this case, this is just a couple of doors. One door is closed, the other closes open. And if I look at this utterance and I look at the contextualizing information, then I can more or less infer that this means close the right door. But what are the inferences that we need to be able to disambiguate this? And what are the symbols that they are defined over? So in this case, symbols might be simple things such as concrete objects, so things like doors, attributes of the door. So a door can be closed, a door can be open. And for me to close the door needs to be open in the first place. But how does this look when we think about social discourse? So let's say that we have an utterance that says something like, we demand justice. Now the real world context is way more complex. So we're not thinking now about just the physical world. This could be, let's say, events that are going on, or information about who the speaker is. So if I know, for example, that the person that made this statement is a conservative politician, and he's talking about this in the context of the Michael Flynn trial, I can infer that maybe we demand justice means something like release Michael Flynn. But what are now the inferences that we need to be able to disambiguate this text? And what are the symbols that they're defined over? So we are moving from the space of maybe concrete objects to maybe some more abstract objects. And I want to motivate neural symbolic methods in these types of scenarios. And I'm going to dive more into that going forward. But before that, I want to take a look at sort of what is out there in the space of language representation. So we can go from the more symbolic to the more neural. So if we think about the most symbolic thing that exists out there, we think about rule-based methods, right? So if we really encode all sort of knowledge, explicitly using symbols and inference rules, then we're living in this space. So then with the boom of sort of statistical methods for language, we kept some form of symbolic representations, but we replaced a lot of these components by learning sort of statistical patterns from data. And in this space, there was a lot of work in, let's say, trying to write declarative rules on top of statistical models that would enforce dependencies between different decisions, or, a lot of space in the work of graphical models, and how we could use graphical models to model dependencies between different decisions and sort of model in these uncertainty. If we go to the more neural, then there's this space of sort of distributed representations of language. So things like, word vectors that try to capture the semantic relatedness of work in this distributed space. And then we moved on from word vectors to contextualized embeddings, in which we now look at the context in which, and this linguistic context in the sense of where the word occurs, and then change the representation depending on that. So if I'm talking about, a bank in the context of, a park, or a bank in the context of, some sort of money transaction. And then from there we move to large language models, which are essentially sort of architectures to build this contextualized representations by looking at sort of co-occurrent patterns between words, and use this sort of like massive amounts of attention heads to try to capture this information. Recently, there's been, in the space of discourse, an effort to bring back some of the symbolic structures of meaning that we worked on a lot before, and then trying to learn representations for them using things such as graph neural nets. So they have a symbolic aspect in the sense that they, let's say, well, I'm going to build a graph structure of whatever sort of a scenario or event I want to model, but then I use a neural net to learn representations for all these components. So there's a lot of work in, for example, in narratives in this space, in which people try to build these sort of graph structures of narratives in which they explicitly model interactions between characters or temporal relations between characters, and then use graph neural nets, to learn embeddings for all of these things. And then in the middle, there's been sort of two trends of work that try to sort of combine or pull a bit closer lessons from the symbolic and the neural part. And some of this work is doesn't come necessarily from the NLP community, but comes from the broader AI and machine learning community. And there's been an effort to propose this sort of general frameworks for combining neural and symbolic representations. And there's a lot of different flavors of how to combine them. However, a lot of this work doesn't really deal with language. So they're usually thinking about neurosymbolic methods in knowledge bases or places where we have sort of a space of symbolic entities and relations. And then we use neural representations to either learn embeddings for these things or to perform some sort of differentiable inference on top of it. And then in the NLP world, there's been a lot of sort of domain-specific solutions. So people that look at a particular task, let's say multi-hop, question answering, and then try to develop a solution that brings some of these ideas of the two things. But really, they haven't been sort of generalized in a way that can be applied to a lot of tasks. And we struggle trying to sometimes take some of these ideas and apply to this, let's say, discourse scenarios. So our goal then was to come up with some neurosymbolic models that were more general and they were particularly suitable for discourse. And the goal is that they can, for example, allow us to model the broader context, that surrounds a language event. And we saw a little bit of it in that example. So, if we're talking about events that are going on or who's the author and how does that sort of tie to the social context that surrounds a particular language conversation. And then also allow us to model symbolic structures of meaning in discursive text. So we know there's been a lot of work, in the space of, learning symbolic representations of, semantics or symbolic representations of narratives. So is there a way that we can leverage those symbolic structures while still combine them with some distributed representations? And then also allow us to incorporate domain knowledge and then leverage maybe some relevant conceptual frameworks that come from domain expertise when we're trying to model a scenario. And I'm going to later talk about one of these examples in which we take, let's say, a conceptual frameworks from social psychology and try to incorporate some of that knowledge in the form of declarative constraints for a particular task. And then essentially the main goal, which is to integrate the strengths of symbolic methods and expressive neural representations, such that we take, some of the strengths of both of these worlds. And our solution was to develop Derail. Derail is a general declarative neurosymbolic framework that was designed with NLP in mind, and particularly with discourse in mind. And we've really spent a lot of time working on this framework and also testing it across diverse scenarios. So for example, we've used it to model long narratives and character arcs and interactions between characters in a particular narrative. We've used it to model conversations, both things like structured debates or, conversations on Reddit and collective behaviors within the participants. We use it to extract argumentative structures. So let's say, we have an essay, for example, that has some long argument, and we want to create some of a tree-like representation of how claims are being used and sort of constructed. And we've also used it to use of symbolic structures to explain discourse at scale. So let's say, for example, we look at all messages posted by liberal and conservative politicians surrounding a particular topic, and then we want to devise some symbolic structure that synthesizes, the main points that they're talking about and what sort of arguments they're emphasizing. And then lastly, we also look at specialized, highly structured domains, and we've done some work on, let's say, looking at technical documentation written in natural language, let's say for networking protocols, for example, and then try to use it to extract a symbolic representation of the behavior. Let's say, for example, the state machine that is being described in that document, or a partial form of the state machine, and then use that for some sort of security task, like for example, generating attacks against that state machine. So this is how I'm going to structure this talk. First, I'm going to introduce the Derail, but I'm going to use it to show how we can model context that surrounds a particular event using this neurosymbolic framework. But then I'm also going to look about another scenario in which we try to model some discursive structure of meaning using neurosymbolic methods. And then lastly, I'm going to talk about briefly about some future directions. So to start, I want to sort of motivate one example. So let's say that we're trying to understand debates online. And this sort of like debate network looks like that. So a person comes and writes a claim that they want to debate in natural language. So it can be something like limiting gun sales is unconstitutional. And then people come and write arguments, either supporting or attacking that stance, to sort of, provide an argument for or against that. So we are moving away from issue-specific stance prediction that has been studied largely in the NLP literature, in which we have a specific debate, let's say gun control, and we want to identify whether something is pro or con. And we're now essentially looking at the textual inference task, in which the debate is a more nuanced point of view that is described in natural language. So it doesn't necessarily be pro or against gun control. It can be some form of control is useful, or should we ban a particular type of gun? And then we have sort of the broader context that comes into play. So then we have the author, that comes in and produces this text, and we may have some sort of broader social context that surrounds this author. So in these networks, the way it works is that someone poses a debate, people come in and start debating that topic, and then other people come and participate. But the way to participate is not necessarily to only write an argument. People come in and sort of endorse different people. So think about this as a like, in Facebook, when two people are debating something and someone comes like, oh, I endorse this point of view, I give it a like. So this induces sort of this like voting style network, surrounding this event. And then we might have some information about some of these people that they've sort of disclosed, about themselves in this platform. Let's say some higher level issues that they might support or not support. But this information is very sparse. So not everyone, fills in this information. So if we think about it, this results in several reasoning tasks. So we have a textual inference task, in which we want to know whether a post or an argument written in text supports or declines a particular claim. We have an author to text relation that encodes who is likely to write a claim, or who is likely to write an argument that supports or attacks that claim. And then we have this sort of social user-user relation that encodes whether someone is likely to agree with someone else, or someone is likely to vote for another person. And clearly there is structure to be exploited. So these things are not independent, they're sort of all related. A lot of times it's easier to think about structure in a declarative way. So if I have a language in which I can define entities, relations, and probabilistic rules that sort of define these interdependencies, I can replace, let's say, standalone classification task across all of these dimensions with an inference procedure in which all of these decisions need to agree with each other to support the overall decision. So for example, I have, the textual inference task, and this, I can encode in a symbolic predicate such as is pro user claim, which is something that I want to predict. Then I have another prediction that is, for example, the agreement between two users. And then I can say, well, if these two things are likely to occur, then it's likely also that this person is going to also be pro that particular claim. So we can use this sort of, probabilistic inference rule to encode dependencies between different decisions. And in this space, this should remind you of things like Markov logic networks or probabilistic sublogic, in which people have come up with these declarative languages to express these dependencies, which essentially define a probabilistic graphical model, in which then we learn sort of weights, to learn the strength of each of these dependencies. But that's what PSL and MLN do. But how do we want to enhance that? So we also want to enhance these methods with some distributed representation to also characterize the context through the representations. So while I have this sort of symbolic inference rule that is associated to a weight that I learned to capture the strength of this dependency, I also want to learn an embedding for each of the components in this problem. So for each entity and each relation that I have there, I want to learn a distributed representation. And then I would like things like this to happen. For example, I want the embedding of a claim that is made by that encodes a liberal point of view to be closer in the embedding space of the liberal users, and the same to conservative users. So in this case, this sort of like, the standard sort of neural net world in which I want things that are related to each other to be closer in the embedding space. And our solution to put two things together is Derail, which is a declarative deep relational learning framework. So from a declarative sort of language point of view, is essentially just like PSL or like probabilistic sublogic. So I have this language of entities, relations, and probabilistic rules that I can write. And then rules represent essentially a graphical model that captures this dependency. These are software, so I have a weight associated with each one, which is going to represent the strength of that factor in the factor graph. But then how do I learn those weights? And this is where representation comes into play. So what I also want to have is entity and relation specific encoders that are reused across all of these rules that serve as a way to learn embeddings for all of these components. And then to score them, I have sort of a rule layer or a rule scoring function that is a composition function on top of this entity and relation embeddings, in which I learn the weight that is going to be associated with that particular factor in the factor graph. So this way I have, a graphical model on top with neural potentials, and each potential is associated to a neural net that is described over this space of sort of relational representation of the world. So in this case, this looks similar to sort of a multitask framework in a way, in the sense that I'm going to reuse the same representation across different sort of classifiers that each for their rule. But then at the same time, I'm putting all of these decisions together in a factor graph to score them together to sort of learn the overall assign. Yes?
So are they pre-trained or you're learning every box with response all at once?
Yeah, that's a great question. So both. So you can either pre-train them and then put them there and keep updating them during your global function, or you can learn them from scratch. In practice, we find that it's better to learn them locally first and then sort of keep updating them because it gives you sort of a better starting point. But yeah, you can essentially do both. So inference looks like the way we would do in PSL, right? So all of these rules define, so you can write them down as linear inequalities that correspond to the disjunctive form because they're essentially horn clause style rules. And then each rule defines a potential that can be added to a linear program or an integral linear program. And on weighted rules, you can also have to enforce, let's say, hard constraints. So you can have some rules that say, I don't want to learn a weight for this. I want this to always hold true. And then you define it as a hard constraint. So inference weight, like if you do exact inference, you pay the cost for it. In practice, if your graph is not too large, you can afford to do that. If that is not feasible, then we offer sort of relaxations to it. So an LP relaxation of an 80 cube style algorithm to relax the linear program. So then the symbolic part is essentially, the same you would have in PSL, but then the neural part comes from the weight. So that weight now is not just that single weight that you keep learning, but it's associated to all of this like neural scoring functions that I showed you. And then learning is essentially a structure prediction framework. So I have, a bunch of rules associated to a neural net in which I can derive scores from. And then I can run this inference, maxima posteriori inference procedures that I showed you in the previous slide. And then I can just have sort of a structure objective to look at the loss between the inferred structure and the goal structure coming from the training data. And then I can propagate back the information, to the neural nets. So here we show the structure hinge loss. So what you would do for a structure SVM, for example, but we also explore with using sort of general CRF loss or some approximations to the CRF loss, and they've all worked pretty well. So you're not only refining, the weights of the rule the way you would in your probabilistic topologic framework, but you also keep updating the underlying representations. So the sense is that you keep learning how to represent all of these entities and relations that you have in your framework, and hopefully you're able to capture also some of these dependencies. So I'm going to show, some results of how this work in this particular case of the debate network. So if we remember, we have this thing down here of what the debate network looks like. So we have a debated claim. We have some posts that people come, and contribute. And then we have all of these different interdependent decisions, right? So we have whether, the decision of whether something's pro or against something. We have the vote for relation. And then we can add other factors to this. So for example, we can make an explicit prediction about whether a user is liberal or conservative. And then we can encode some of those dependencies as well, right? So if you and I are likely to agree with each other and I'm liberal, then it's likely that you're also a liberal. So we use sort of all of these things, all of these factors together with this dependency. And then here's some results of how we do of course, the 3 tasks that I introduced, right? So the textual inference task, the user to text task, and the user to user task. So the baselines that we use there for the first one, the purple one, is just what I can do if I just have standalone neural classifiers for it, right? So each of these decisions are independent, and I just use a neural net to score all of those decisions by themselves. Then the blue part is what happens when I share some embeddings, so I have that relational embedding space that I showed, but I remove the explicit inference. And we can see that, that is pretty good for sort of the social relations, but it doesn't do as well, in the textual relations. But then now when we use the explicit inference, in the case of the green one, we use PSL. And in this case, the way we introduce the neural functions is that we just pre-train them locally and then introduce those weights as priors, and then let PSL learn the rest of the weights. And that's as far as we can do by doing that. And then the orange line is when we now keep updating the representation, right? So that's with Derail. We don't only pre-train the weights to introduce as priors and then, learn to weight all the rules. We keep updating the underlying neural functions and the underlying representation. And then we're able to, consistently get some performance. Some background about this. These are tenfold cross-validation across a bunch of different debate topics. And we found this to be statistically significant. And then the other thing that is sort of neat about this is that now we have this sort of big distributed representation of all of these components, both the raw things such as the text, but also we have an embedding now for all of the symbols that we created. Let's say, for example, we found embedding for the liberal and conservative symbol. And then we did this fun experiment in which we look at the embedding of the symbols of liberal and conservative, and we look at the claims that are closest in the embedding space. And in this case, it's some example about LGBTQ+ claims in these topics. And keep in mind, these were all debates, so it's why when same-sex marriage was being discussed. And then we find, for example, that the embedding, the statements closest in the embedding space to the liberal symbol were all unsurprisingly pro statements, so things, supporting same-sex marriage. But in the case of the conservative symbol, we found more of a mix of things. So we had both things that were pro same-sex marriage and things that were against same-sex marriage. But one of the things is that they had in common is that they tended to emphasize this sort of morality aspect. So you had statements such as whether gay marriage was bad or not bad, or a sin or taboo. Whereas on the liberal side, we have all of these legal statements. So things like it should be legal, it should be a right that is given to people. We did a similar, experiment with the claims around the gun debate, and we found some seminal patterns. So in the closest to the conservative symbol, we found really sort of like bold statements like no law should ever restrict the right to bear arms. And then on the most liberal side, we found the opposite, right? So the US should ban most guns and confiscate them. And then in the middle space of embeddings, we found more nuanced points of view. So something from, some form of gun control would be good for society, or a particular type of gun should be banned. So we can see that, at least in the sort of close to the symbol, we could capture also these dependencies through the embedding space. Take a look at how we would do, or if these representations would generalize to statements beyond the data that we were looking at, we downloaded statements made by 3 prominent politicians and tried to score them with the model that we'd learned on this online debates. So we downloaded from ontheissues.com statements made by Bernie Sanders, Joe Biden, and Donald Trump, and try to score them using our model. And we were able to sort of recover their relative position in the political spectrum. So we have, Bernie Sanders mostly on the left, Donald Trump mostly on the right, and Joe Biden on the left, but taking a more moderate stance. And you can see that, there's some stuff that you wouldn't expect there. So there's some portion of red for Bernie Sanders that you wouldn't really expect to be there. Some of those things are errors that we have in our model, but some of the other things were also some nuanced sort of statements that were being proposed by these politicians. And there's some examples here of those. So for example, we can look at Trump, and we found a left statement for him in the context of abortion. And it was a statement saying something like, Planned Parenthood does great work on women's health, which is a statement he made before running for president. So we can see that, it does happen, that we have sort of these nuanced statements that don't necessarily align with the overall view of the politician, but that we can capture using these representations. So to finalize this part, I want to show sort of how to evaluate the different modeling choices. So beyond the overall results that we had, that, okay, so if we use inference, we do better. If we use inference for representation, we do a little better. We did this experiment by reducing the amount of textual supervision that we had, and then try to leverage the contextual information that we had. So all of this sort of user-to-user relationships and agreements. So we looked at how each of the components of the model contribute to this. So if I have 0% of textual supervision, if I just have a standalone classifier, then obviously I can't do anything. So I can't predict anything from these claims and whether they're pro or con a particular post. But then if I exploit social context during inference, even when I have 0% of textual supervision, there's something I can get just by exploiting this sort of relationships between people. If I expand that inference with also some embeddings, so this shared representation across users, then I can do even better. And then this trend sort of maintains itself the more mode of textual supervision that we add. However, the impact is reduced, right? So the more textual supervision that I have, the best I can do with the standalone model. But when I have really limited cases, then really leveraging this sort of contextualizing information really helps me. Which is an argument, for expanding methods with sort of these dependencies in cases where you might not have access to direct supervision. So I'm going to take a little. Okay, so we looked at Derail, and we looked at how to use it to modeling the context that surrounds, let's say, a conversation. But now I want to also look at to model some symbolic structures of the text itself. So I'm going to do this idea of understanding discourse at scale, which I really think it's a natural fit for neural symbolic representations for 3 reasons. First, you have a lot of text coupled with behavior, in let's say, online debates or conversations on Twitter. There's also a very dynamic domain. So it's a moving target for supervised learnings, because what people are talking about today is not necessarily what people are talking about next week or 2 weeks from now. Then there's also the rationale of people's statements or people's opinions really rely on complex concepts. So we saw a bit of that. So things like ideology, interest, arguments, and many more of these things. But then if I had sort of this way to make this explicit inferences, I could do things like, well, if you're talking about healthcare as a human right, then it's likely that you voted in favor of Obamacare. And these are sort of behaviors that we can capture using sort of the symbolic structures. So if we think about it, a lot of opinions are really grounded in morality. So if I see a statement like this that says 6 years later, healthcare costs have increased, skyrocketed, and millions have lost access to their doctors in the context of Obamacare, I can clearly know that this person is not a fan. But what are the right abstractions of this tweet that capture sort of this stance? If someone says millions have less access to their doctors with Obamacare, they're framing Obamacare as something that is harming people. There's been a lot of work in social psychology in sort of organizing human morality across sort of foundational dimensions. And this is sort of the moral foundation theory that emerges from evolutionary, cultural, and social origins. And they sort of capture these sort of higher level principles that guide our moral understanding of the world. So one of these principles is the principle of care and harm, which has to do with the idea of generosity, compassion, and sensitivity to people's suffering. They have the principle of fairness and cheating, so things that have to do with justice, reciprocity, rights. There's this principle of loyalty and betrayal that has to do with in-group affiliation and solidarity between sort of people in the in-group. And then things such as self-sacrifice and patriotism tend to be related with this. Then there's the principle of authority, of subversion, that has to do with fulfilling social roles, authority, hierarchy, and tradition. And then lastly, sort of this principle of purity and degradation that is associated with the sacred and holy, that has a lot to do with religious principles, but not exclusively so. Moral foundation theory has been repeatedly used in the social sciences to explain behaviors. In the case of US social politics, for example, they have found that liberals tend to emphasize fairness, while conservatives emphasize things like loyalty and authority. However, everybody cares. So there's some moral foundations that are really being used equally by both groups of people. However, they not necessarily care about the same things. So if I have these two statements made by one a conservative politician and the other one a liberal politician, both in the context of Obamacare, they're both really using the care ham for moral foundation. But in the first one, they're framing small businesses as the target of care, which is a very conservative talking point, whereas the second one is framing the Affordable Care Act as the caring entity for millions of Americans, which is a liberal talking point. To capture this, we define morality frames, which is a symbolic structure that tries to capture these dependencies and the differences in the actors and targets of moral sentiment, and then being able to tie these things to other aspects. So the way the frame looks is very simple. So you have an overall moral foundation that is being sort of elicited in the text, and then you have entities that play sort of the actor and target roles in here. And they also have some sort of associated polarity, right? So whether you're taking the role of the carer or the harmer. And then this provides like a convenient frame for then now tied to other types of judgments. So for example, I can say, well, if the target of care is immigrants, then the author is likely to be a liberal. Or if the causer of harm is immigrants, then the author is likely to be conservative. And then we can really use something like Derail to model something like this. So I can start with just some base classifiers, right? So I have a nice classifier that uses something like, birth or whatever is your favorite sort of neural classifier, and I map text to a moral foundation or text and an entity to a specific moral goal. But then I can also define rules that capture other dependencies, for example, party messaging preferences. So what is the likelihood that when someone's talking about a particular topic and coming from a particular ideology, are they likely to take a particular moral foundation or a particular entity role? And then it can also capture things like party consistency preferences. So if I have two authors and they're both from the same party and they're talking about the same topic and talking about the same entity, then they're likely to have the same polarity, regardless of the moral foundation that they use. So for example, liberals are always likely to portray the Affordable Care Act in a positive role, even if they're talking about care, harm, fairness, cheating, or whatever other moral foundation. So we use this model in Derail to sort of model how good we were at predicting moral foundation and the morality frame roles. And we did a similar analysis as we've done before, right? So we start from a lexicon approach, which is what a lot of social scientists do. So they've developed this really curated lexicons of what are things that are likely to elicit moral sentiments, but they really sometimes break when you move them, to a different topic and so on. Then we have some annotated data so that we can learn an end-to-end sort of neural classifier for this. And then we have sort of a multitask framework in which we decompose this decision, in these different rules, and then we share the internal representations to do it. And then that's sort of as far as we can go with that. And then we have the two same setups that I showed before. One is PSL, in which I, use the neural nets to get some weights to score at priors. And then lastly, with Derail, I keep updating the internal representation. And then we found a consistent improvement. And it's not only really about, how well I can predict this, but now I have this sort of symbolic structure that serves as a way to explain discourse at scale. So we took a look at and downloaded all tweets made by Congress members on the topic of abortion, and then you predicted these morality frames to analyze the discourse. And then we looked at the most frequent entities and their most associated moral roles, and we found some interesting things. So while there's some variation, on the entity usage, we found some entities, for example, women, that were really used by both groups a lot. However, the moral roles that they used were very different. So if we're talking about a liberal politician, they're likely to portray women as the target of fairness and cheating, where conservative politicians were more likely to use women as a target of care and harm. And then we can use this sort of symbolic structures to induce this sort of entity relation graphs to sort of capture the common topics that people discuss around this topic. So we have, in blue, the most frequent target entities, in green, the most frequent caring entities, and in red, the most harming entities. and then both for conservatives and liberals. So it provides this sort of like nice sort of symbolic structure to look at the differences between the discourse. If we think about topics like abortion or gun control, the discourse is pretty stale, right? So both parties have their arguments that they repeat over and over again, and there's really not a lot of movement. But this is really not the case with everything. So to look at more dynamic domain, we'd look at tweets made by Republican Congress members before and during or after the US Capitol riot. And then we look at some changes that we could find in entities during this time. So if we look at before, things look really like the usual, right? So you had things like Congress and Trump on a positive role and positive roles, and then things like Democrats and Pelosi on negative roles. But then we found that during this event, the entity of Trump started to take a more negative moral role throughout the conversation. And it happened because a lot of politicians conservative politicians were sort of switching to a more critical discourse about the role Trump had on not conceding the election and sort of how he was handling the riots as they were happening. And the same thing happened with the Democratic thing. So we also looked at a change in the moral role that certain entities would take. And while before things looked very polarized, like the way you usually would, then during the event and after the event, we started things like Michael Pence started to take a positive moral role, which was something that didn't happen before. And it had to do with this idea that Mike Pence was sort of pushing towards accepting or conceding the election. And then another impressive change was around the police. So right before this event, we had this sort of Black Lives Matter protest, with a lot of the liberal discourse was essentially critical of the police. But during this event, they started to sort of, portray police in a more positive moral role because they were sort of helping take care of the situation in the Capitol. So it really provides a sort of like nice framework to look at these changes and, look at what things happen before and after a particular event. So I'm going to do another. So to sort of finish this, I want you to think about what happens when we're moving, from this morality frame sort of structure and try to turn this into a more holistic opinion analysis framework. So when we're talking about politicians, the advantage that we have is that we know where they stand, right? So I know who are the conservative politicians, I know who are the liberal politicians. So knowing their stance on particular issues sort of comes for free. But if I move this to the general public, then I need to augment this with new predicted categories. So now, for example, let's say that we're trying to look at the discourse around the COVID vaccine. So then now I have to also augment the moral frame analysis with some opinion analysis. Let's say, for example, predicting, whether a statement is pro or against the vaccine. And then maybe expanding that with some sort of overall reason provided for why someone would be pro or against the vaccine. If we think about it, these things are really interdependent, right? So if I'm looking at this example, for example, in which I really see the moral foundation of oppression being really present, and something like government taking a negative moral role, is very likely that then the vaccination stance is going to be negative. And also that among the possible reasons, maybe government distrust is one of the reasons that is being offered for not trusting or not believing in the vaccine. So we actually annotated some data around the COVID debate across these different sort of analysis dimensions. So we have morality frames like we did before. So we have the moral foundations and the entity role. But then we also have now stances, with respect to the vaccine. And then we augmented this with reasons. And to do this, we built on previous work by health informatics, in which they manually coded sort of 12 main themes that are used by people to refuse the vaccine. And then we grounded them in text using sort of sentence embeddings. And then we looked at the correlation matrices between the reasons and stances, reasons and moral foundations and stances. And we found that a lot of patterns emerge. So for example, if people are using the authority subversion frame, they're more likely to be talking about an anti-vaccine point of view. Or if people are talking about the vaccine being against religion, this is likely to elicit sort of the purity degradation moral foundation. So if you think about it, you can also model this type of thing using Derail, right? So it looks similar to what we did in the morality frames, but now we have more base classifiers, right? So we have more decisions to make. We have now to predict the stance or to sort of score the main reason. And then we can explicitly represent dependencies between the different decisions. Even if we don't know exactly which ones map, we can try to learn sort of this correlation matrix that I showed. And then also we can enhance this with these other things like consistency preference that we saw that were useful before. So if two people, are anti-vaccine and they're talking about the same entity, then they're also likely to be using the same role. And we did, sort of the same experiment that I showed before. So I started with a lexicon-based, morality lexicon. And then we have now two base neuroclassifiers. One is a direct supervision one with this sort of annotated data that we collected. But the other one, we try to do the indirect supervision one because we wanted to test how, when we move from one domain to the other, how likely are we to be able to reuse sort of this annotated data to predict that? So maybe now I want to analyze another domain. I don't want to re-annotate, for morality frames. How well can I do when I just use the political data that I had, right, to predict that? And then what happens when I combine those things using Derail? And then I got, we got quite a impactful improvement, particularly in the case of morality. We worked really hard initially to predict using in this COVID data. And then talking about distance supervision, one of the questions that we ask is explicitly modeling these dependencies between all of these analysis dimensions, helping me when I don't have a lot of direct supervision to rely on. So what we did is that we again reduced the number of direct supervision that we had about the COVID debate. And I start with distance supervision. So distance supervision in this case is trained on that political data that I showed before for morality frames. And in the case of stance, this came from, let's say, common hashtags that people use pro or against the vaccine. And then we developed a noisy data set to score that. And then we started to add, we added the explicit dependencies between the different dimensions. And then we slowly increased the percentage of direct supervision. And then the dotted line is how much I can do with a base classifier, a standalone classifier with 100% direct supervision. So what I found is that symbolic inference makes our model competitive with just 25% of direct supervision. So the fact that I have all of these sort of different decisions that inform each other allows me to correct cases that I might not necessarily get right with the different weak supervision sort of classifiers. And then also we're able to beat the fully supervised base model with just 50% of direct supervision. So this is similar to the other results that I showed before when we reduced the percentile of textual data. And it's again sort of an argument to leveraging these interdependent decisions to deal with complex cases in which we might not have a lot of direct supervision. So this is what I have for now as far as previous work goes, but I want to spend a small amount of time talking about some potential future directions. So the first one is sort of this idea about machine learning, about essentially a way to communicate knowledge from humans to machines. So currently this is done in a very inefficient way, right? So we usually just label examples and then learn, classifiers from these labeled examples. But the truth is that the bandwidth of interactions can really be much greater. And humans are great reasoning machines. If we had a way to characterize learning problems by using intermediate concepts that might be shared, across different domains and across different tasks and dependencies between them, we can probably generalize, across this. And we saw a small flavor of that, by using this sort of general morality framework that we could use both to analyze political discourse and COVID information. And representing these dependencies really helped us deal with this limited supervision settings. So let's go back to sort of this holistic analysis framework. So we knew how to do that using indirect supervision because we have some annotated data. We did hashtags for the stances, but for reasons really, we relied on previous work that told us these are the main reasons that people use when they want to refuse the vaccine. But what happens when we don't really have a predefined list of reasons to rely on? So we started to take a first step towards that by building sort of a human in the loop interaction protocol in which we start with, a lot of data, and we have this model that puts all of these different decisions together based on some, other data that I have and some classifier that I have. And it gives me an initial breakdown of different sort of themes that come up in the data. And then we can provide some visualizations for people to explore these things and then have some informed discussion about what they see. We're here we're thinking these people are domain experts, right? So maybe some social scientists that is trying to make sense of these data. And then they can, have a discussion and then propose interventions to improve this model. So it could be, augmenting some of these inference rules and telling me, well, this cluster that I see right here really evokes an anti-vaccine perspective. So I want, all of these tweets right here to be anti-vax. Or I can say, well, these are not one cluster, these are actually two clusters, and I name them, for example. So really, we're combining a bunch of things, right? So we're combining machine learning NLP techniques. We're combining sort of interactive interfaces to visualize and make sense of data. And then we're also leveraging some qualitative methods. So there's a discussion phase in which humans look at these data, talk to each other, and do some form of thematic analysis to propose these interventions. We did some initial experiments by taking a look at how much this type of interaction would help us to improve the correlations between the different analysis dimensions. So we start with a sort of fully unsupervised way. So I just have a topic model that I plug in the data, and then I try to see how much it relates to something like a moral foundation. Then in the middle is what we got from previous work, right? So they gave us the reasons, we instantiated in data using sentence embeddings, and that's what we get. And then here's what happens when we actually interact with people and have them sort of refine the reasons. And we find that we are able to increase sort of the strength of the correlations between the themes and the moral foundations. And the same thing happens with stances, right? So we are represented using heat maps, and you can see that you start to see more strong colors, after the interaction. So where to really go next? I think that we can really get more out of this interaction. And I think that neurosymbolic representations can help us here because they have these two advantages, right? So symbolic symbols allow us to manipulate concepts and their interdependencies directly, whereas neural methods allow us to ground all of these symbols in text because we have sort of this, embedding space that lets us manipulate things. And I think there's a lot of impact for, things like debiasing data sets or dealing with concept drift and cross-domain classification when using these types of techniques. And really, there's a lot of applications to challenging real-world scenarios that we can have here when we really need to elicit some knowledge from people. And there are two main scenarios, that I'm briefly going to go over because I know that I've been talking for a long time. So the first one is sort of leveraging richer sources of knowledge. So things like, technical documentations, legal text, really sort of structured, knowledge-rich information that has a lot of specialized vocabulary and where a lot of domain expertise is needed to sort of understand what we have here. And they're really highly structured. So there's like formal definitions of concepts, a lot of procedural descriptions, and so on. We've done some initial work in this space in which we try to read technical documentation and try to derive some sort of symbolic structure that we can then use. So for example, we have an RFC that describes a protocol in text, and we can leverage, let's say, large amounts of unlabeled textual information about networking protocols that it's online. Things Stack Overflow, textbooks, all of this information that you can get out there to learn a technical embedding. Then we also have structured knowledge and resources. So we have the actual RFC that, talks about this concept, describes them, and talks about procedures. And then we can model behaviors and expectations using this sort of symbolic structure. In this case, we're thinking about, let's say, a state machine. And then we can use the state machine for real world applications. So in this paper, we use partial state machines to do automatic attack synthesis. But this was really just sort of one example of what we can do with something like this. And then the last one is essentially just modeling richer sources of context. So there's been a lot of work now in NLP to try to combine sort of visual and textual modalities by trying to identify the same concept both in the visual sort of form and in textual form and align the two of them. But if we think about it, context comes in multiple modalities, right? So we have the visual world, the auditory world, the spatial world, formal representations, and the social world. So can we think about concepts and symbols that represent these concepts as intermediate representations that allow us to sort of walk between these modalities and reason over these concepts? And my example here is, let's say we have a narrative. Let's say it's a short film, for example, in which we're trying to track the arc of a character. And then we want to model explicit motivation and emotions of these characters. We can build in some social context or some social sort of conceptual framework like we've done throughout this talk to try to learn and predict motivations and emotions. We can explicitly model dependencies between these, right? So depending on what my initial motivation was, that's likely going to affect, the emotions throughout the story. And then emotions could be, let's say, grounded in some auditory signal. So the prosody, or the strength of the sound can really help us, tie these things together. And then let's say we want to, predict what is the more likely next action of the character. And this can be tied, to sort of all these other symbols or abstract concepts that we talked about. And then this also can be grounded in other modalities. So things like the visual representation of the action or the spatial world. And that's really all I have for now. And I'm happy to take any questions. Yes.
Really impressive stuff. So the derail, that was your method where you had both symbolic constraints and then learn weights. Is that the idea?
Yes.
And so I'm a machine learning person. I'm on the method side. Other than, I guess, concept drift as an open problem, what is sort of directions that you want to take derail, or is there like any room for improvement? It seems like it's highly applicable, but on the methodological side, are there ways you'd like to extend it?
Yeah, I think there are a lot of ways. So we really explore just one way to combine sort of neural and symbolic representations, but I think there's like more room there. So the way we did it was like, okay, we say we have the symbolic, rules that really builds on things like PSL, and then we have now a distributed representation of these things. And the way we put them together is now derive those weights from a neural architecture. But I mean, there's a lot of people working on, can we expand this type of sort of correlation analysis with some causal, type of symbols. That's one thing people are looking into. Other things is, can we do more explicit logical reasoning? Right? So we are just doing, we're doing this in a graphical model, but can you expand this to, some explicitly reasoning steps? Expand the type of logical structures that you deal with. So I think there's a lot of room in that space as well. There's this other camp of people that try to also be more intentional about the way they impose this symbolic constraints in the representation. We just essentially just left it as, so we have this modular representation of these components, but all of our reasoning or all of our inference is really done in the symbolic space. So, is there a way to, put some of that back into the representation and really, encode some type of particular learning objective that encodes those dependencies, or that really lets you test it? I think that's another avenue there. And then, a lot of people don't really like to do this explicit symbolic inference because they don't want to, it's like if you have really large graphs, then you have all of this sort of computational considerations. We're doing explicit symbolic inference. In our case, that doesn't really happen because our graphs are sort of small, but I'm pretty sure that you run into way more challenges if you're trying to deploy this in like a really large information network. And then you might, have some challenges that come into that. So maybe you can't really aggregate the gradient the way I do, to sort of backpropagate back to all of that. And you really have to come up with ways to learn those representations. So I think in that space, there are a lot of challenges as well. Yes.
So I'm not a machine learning person.
Yeah.
And I've always wondered, how do you do apples to apples comparison? Like you have your 4 bars with your neural net and this and that and the other. How do you make that comparison? This is a really elementary question. With a neural net, when you train the neural net, aren't there like a zillion choices in how you train a neural net?
Yeah, so that's a good question. So what we did to standardize that is that we use the same neural architectures across all of those tests. So we essentially, sort of say, okay, we are going to represent this decision or this factor using this neural net. And then that's the same one that we use inside sort of the symbolic method to represent the thing. So we standardize that. And that's the way we went around. So maybe, you can find another, composition of that net that's going to be better, but you can make the argument that, well, then I can plug that in and derail as well, right? And hopefully then you get an edge. We found that in all of our experiments, that translates. I'm sure there's going to be an example in which that doesn't happen anymore. Our worst case scenario, it never really degraded the performance. What we did find is like, we have a rule that maybe didn't really help you anymore because the neural net was already capturing that. I don't know if that's the right, hypothesis for that, but it did happen that, I have a rule that I expected to be really useful because it had a really strong assumption, and then adding it really didn't do anything. But we always do, in the papers, we have this like large ablation studies in which we turn off and on all of those rules and see, which one contributes to what. So you can really see, where is your impact by putting these things together. Yes.
It seemed like in a lot of the results, the PSL did really well.
Yeah.
It was like second place.
Yeah.
And then the neural addition got you to derail, got you a little bit. So the advantage of symbolic models is explainability.
Yeah.
Did you come to any insights where there was something that PSL was getting wrong and now it's getting it right with the addition of the neural weights? And it's like, oh, this was going on.
Yeah, that's a great question. And we did find, at least, I think that's translatable with both PSL and Derail, which is essentially, when you can really know the impact of each of the inferences that you add, and you know how much they contribute into it. I really didn't come into any case in which PSL didn't work and then Derail worked. It was more like Derail did it better than PSL would have. But I think they were pretty strong at capturing sort of the same information. So you really have that sort of like usual, standard thing. What we did find is that PSL can take way longer to train because I guess like the neural representation really gave you sort of an edge in which sort of converging the weights of the rules, what's way faster, even though their framework is probably way more highly optimized than mine, or at least they've been working on it for longer. So that I think it's just sort of can hack, PSL to do it because, we gave that weight that came from a neural net, but you really don't have a way to seamlessly integrate that into your framework. You have to do it offline and then just sort of push the weights right there. So one thing that I found really useful in Derail is that I could add some rules that weren't really for anything other thing than learning representations. So I can add additional classifiers with some other data that would capture, something completely different that where they're just for representation learning. And I think that's one thing they can't do. Yeah.
You add pretext tasks.
Yeah. Yeah, so we call it this like auxiliary tasks or auxiliary rules that really weren't part of what you were trying to model, but that would help you bootstrap and learn around representations. And then you can do that in the same framework, which can be really, really useful. I think I have a question from the, yeah, so the Derail code is available. The documentation is not. So I think it'd be hard to use. So, I mean, it was just me alone working on this, so I haven't had the time to write it, but this is my summer plan to put the documentation up so that people can use that. Yes.
I was wondering how much.
Sorry, I can't hear.
So how much improvement in data efficiency?
Yeah, so it depends on the task. So we would always sort of, it was in performance, you say, or in?
I mean, data efficiency.
Oh, data efficiency. Yeah, so we did show a bit of that. So you can see that you can reduce sort of the number of like direct supervision or supervision that you have. And it really does help because you have sort of way more decisions that help you bootstrap the process. So I think data efficiency is like one of the places where it really does shine. We can still take advantage of all the neural stuff. So I can have pre-trained BERT in there already, and get that edge. But then the amount of like maybe data that I need to fine tune it is less than you otherwise would. So I mean, I don't know if that answers your question. So in the Derail paper, we have one example in which we tested that, and it was useful. I don't know if you would translate, to every domain.
Alexis has a question on the Zoom.
Yes.
Yeah, hi, really interesting work, and I'm excited to talk to you more about it. I have a question. So in your set of kind of basic classifiers, right, a lot of the things that those classifiers are doing are pretty non-trivial.
Yeah.
Like mapping a tweet to a moral frame. I wonder if you could say something more about how well those classifiers do and whether you get kind of error percolation in this setup.
So how well those classifiers do is essentially what we have usually as a baseline, right? So for example, here, your classifier, for example, for morality was pretty decent. You could get sort of 55 F1, but for moral foundation, it was really poor. So you were just on 25. And so, I think this makes sense. So morality is essentially yes, no, is it moral or not, which is a way easier task than try to put them apart. So in that case, yeah, it is really bad. And what you get from inference, then it sort of outshines, a bunch, because then you can tie to the other things. And this is sort of the argument, it's like, if you have this sort of really difficult tasks, then can you sort of, enhance them with all of this supporting information in not a featureized way, right? So we can also try to just flatten all this and try to make it a feature vector, but it usually does worse. There might be better ways to break this down. So that the flexibility, the nice flexibility is that you can choose sort of the level of abstraction that you have and how much you push towards the neural representation and how much you make explicit in the inference. So in this case, we're say like, yeah, my base classifier is something really complex, like a moral foundation, but you might want to not do that and then try to make some more like fine-grained decisions over the text and then build on that. But you really do have the flexibility to do that. And I guess that's like one of the advantages of sort of the neural symbolic part, because you can say, how much I want to just let the neural net try to learn by itself and how much I want to be explicit about it.
Nice, thank you.
Any other questions? Okay.
Yes, there actually going to be a reception. Okay.
Sorry, I have a question. I wasn't fast enough
Yes.
with my. So my